Welcome everyone, this is the fourth video of the 11th chapter in the Crystal Clear Electronics video series. In the previous video, we used the pre-written delay function. Now let's see how we can write our own version.
Let's think about what we've learned so far. The microcontroller executes a command in every clock signal cycle. We also know the clock signal frequency, which is 8 MHz. From these two, we can calculate the number of commands that are executed under a certain amount of time. For example, if we have a variable initialized from 0 and we continuously increase its value inside a cycle, then we'll get a counter which steps forward one after every clock signal. All we have to do is move the counter until it reaches a value we have calculated for our desired delay. In our case, the clock signal of the microcontroller is 8 MHz, so 8 million commands are executed each second. Create a variable called counter and increase its value inside a loop until it reaches 8 million. In this case, if we check the variable at the end of every loop, then 1 second has elapsed when the counter reaches 8 million. We can implement a delay algorithm using this method, which can be used if we do not require very accurate timing, just an approximate delay. On the other hand, the delay ms function provides very accurate timing. Let's see an example function. Copy this function before the main function and replace our calls of delay ms500 to our own delay millisecond 500 function.
Let's upload the updated program and see how it works. It is flashing, but it's not the real thing. Why could this be?
As you can see, one period is just under about 6 to 7 seconds instead of 1. The reason for this is we are not only executing one counter plus plus instruction, but also a bunch of other instructions. The order of operations looks more like this. As the first operation, read the value of the counter variable from the memory to the operational register. The second one is to write 800 into the operational register as a value. The third is to execute the comparing operation. The fourth is to jump to the counter plus plus or the time plus plus lines according to the result of the previous operation. The fifth is to increase the value of the counter or the time variable, that is incrementation. The sixth is to write the value of the counter or the time variable to the memory. The seventh is to jump to the beginning of the cycle. It isn't that easy to calculate how much time it takes to run a delay cycle like this. For this reason, it's inappropriate for precise timing as we've mentioned before. If you write 1195 instead of 8000, then the delay will be quite acceptable, but it's still not accurate enough. This number was determined by experiment. It's worth mentioning about the example that the variables may overflow. We know that our variables are stored in finite-sized memory, so they cannot be arbitrarily big. An unsigned 8-bit variable, a type of car, can have a value from 0 to 255. Why would that be a problem? Let's have a look at this number represented in binary to see what happens at the time of overflow. This is the clearest because the processor works in this number system. If you write a decimal 178 in binary, stored on 8 bits, we'll get 0B10110010. Add the decimal 150 to this number, which looks like 0B10010110. If you do the addition, the end result will not fit on a width of 8 bits. However, we store the result as an 8-bit number in memory, so the highest place value won't have a place to go. In technical terms, this is called an overflow, like overfilling water in a glass. In this case, the calculated result will be 72, which is 0B01001000, instead of the expected 328, 0B1010010000. This could cause a big problem with any mathematical operations, so you have to watch out for the variable's range. The table below summarizes the types of variables, their size and range of values. For example, the car type can take values from 8 bits, 0 to 255, or minus 128 to 127. The unsigned car, which is also 8 bits long, can take values from 0 to 255. The signed car, a signed character, is 8 bits long and can take values from minus 128 to 127. The integer, int, is 16 bits and can take values from minus 32,768 to 32,767. The unsigned integer is unsigned int 16 bits and can take values from 0 to 65,535. The long is 32 bits, the unsigned long is also 32 bits. The ranges of these are also given in the subtable. Think about increasing the variable in the previous example until it reaches 8,000 or 1,195. If my counter was an 8-bit variable, then there wouldn't be any problems until 255. Each cycle would increase the value by 1. However, if we added 1 to the maximum value of 255, we wouldn't get 256, but 0 again. This way, the counter would never reach any value higher than 255, and the program would stay in an endless loop forever.
Thank you for joining us. We'll up the ante in the next video, but for now, I'll just tell you that we'll need another LED. See you!
Bye!